Alright, so we're going to quickly go over, well not quickly, but we're going to go over domain and range again, the idea and why we use it. So usually in real world problems, the domain and range is actually restricted, right? Up until now, for domain at least, when we did quadratics, we say it goes on forever. But if you're doing a real world problem, say, right, throw a ball, the ball will make a parabola, which you can use a quadratic equation to express, right? But this obviously does not go on forever. It has a point where it starts and a point where it finishes. And so it wouldn't have a domain that exists everywhere. Same with range. Okay. Now we're still going to be using the form, the vertex form. Okay. We'll look at different forms in other chapters. But vertex form is very, very useful for identifying domain and range because it tells you directly what the vertex is. You can just look at the equation because HK is our vertex. And then what's important is not necessarily the value of A, but whether or not A is positive or negative. Right? If A is positive, then our quadratic opens up. And if A is negative, our quadratic opens down. And that's going to be important in determining range. So let's look at some situations. For example, linear functions. Linear functions, well, if you have a linear function, it's just a line, right? And if that line goes on forever, like this, right, then we are in every single x value going sideways, and we are in every single y value. Okay, so we would write the domain as being XER, meaning x is all real numbers. Okay, and then we have the range, which again is all real numbers in our set, which is on our vertical axis. So that's not too bad. There are some exceptions though. For example, say you had a horizontal line. If you had a horizontal line, well, that horizontal line only has one y value. It goes everywhere to the left in x and everywhere to the right in x, but only one y value. So in that case, it wouldn't exist for all. Similarly, if you had a vertical line, same idea, right? That vertical line only has the one x value, not all. But what about quadratics? Because that's what we really care about in this course. Well, again, if our quadratic goes on forever, let's just take one like this. Okay? These lines never come back on themselves. They always keep extending outwards, this one to the right and this one to the left. So if you were to trace that on forever, you'd eventually get every single point in x. And so we usually say x is all real numbers in the set. Now the tricky thing is y. Now y does encompass all real numbers. Right? We always say all real numbers because we're not talking about discrete points. If you were to plot data as like a point, and a point, you'd have to actually identify what those values are in x and what they are in y for your domain and range, which is what we did in the very first lesson of this chapter. Right? But these are continuous. Because they're continuous, they would exist for any point where the line exists. Right? Even your x value could be 2.187654392, and it would exist there. So that's an infinite amount of numbers to write. So instead of writing an infinite number of numbers, we write that it's all real numbers. But then, of course, it's not all real numbers in y. It's all real numbers within a certain, well, range. So how do you find out what that range is or what those conditions are? So to determine that, we're going to need to know the vertex, like I said up here, which is HK. And we're going to need to know whether or not it opens up or opens down, which is our value for A. So I've said a lot. Let's just try an example. Well, a couple examples anyways. First one, you can probably identify that as a linear function. The reason why you can probably identify it as a linear function is because of the order of the equation. The highest exponent is only 1. So that's a linear function because it's first order. Because it's a linear function, we can say linear, right? It's not horizontal and it's not vertical because we have a proper slope there. So we can just say the domain is all real values in x, and the range is all real values in y. All right, the quadratic. Now in the quadratic, in this case, our vertex is 4 and 1. So that's our vertex, 4 and 1 vertex. Now technically, you only really need to know this value, right, which is our vertical shift. It's our k value. Right? That tells us the y value of the vertex. So if I were to draw the coordinate system, I know the y value is at 1. Now I can do the whole point. I can write 4 and 1 here. Right? So I know it definitely exists at the point 1. But the question is, does it exist everywhere above that point as well, or everywhere below that point? You're not going to have both. You're not going to have a graph that does this, because that's a cubic. That's not a quadratic, and we're not going to be looking at those. It's either going to go up, and it's going to go down. And you can determine that by looking at the sign on your A value. So because it's negative, it's actually going to open down. And it'll keep opening down, 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 down forever. So because it's going to always go to the left and it's going to always go to the right, it'll hit every point on our x-axis. So our domain is all real values. Now the same is true for our range. It is all real values, but only for a certain condition. In this case, it's everything below that vertex, everything below it, because it'll keep going down, but this function will never go above that point. So we say it is for all values which are less than or equal to that vertical shift, or a y-coordinate of the vertex. Does anybody have any questions with that? All right, so our next example, you look at it, you're probably going to notice this isn't in vertex form, so it's a little bit trickier to deal with. Now it is a quadratic, so you might be able to guess, oh, well, then it's probably going to exist in all x values. Okay, but what about the range? You can start by writing all real values because you know it's a continuous function. But what's our condition? And we'll look more at in a later chapter of how to take this quadratic, which we say is in standard form, and we will complete the square and put it into vertex form. But for now, what we can do is use a little bit of technology. And you can open Desmos. I'm actually going to open a new one because I want to look at that later. Okay, and then you can type in this equation, which would be y equals 0.5 x, even though it says t, I'm going to write x because that's what Desmos likes, plus 10x plus 200. All right, so I don't see that anywhere on my graphs. Let me zoom out. There it is. Okay. I can click on that point, and it will tell me the vertex has a y coordinate of 150. and it's opening up. So I know it exists for all y values that are at 150 or greater. So what I'm going to do then is I'm going to write for all y values greater than or equal to 150. All right, so here's some other examples. We have two examples of graphs. One's a line, one's a parabola. Okay, and we have to write the domain and range. Now this one, notice that it does not have arrows. If it goes on forever, you usually put arrows, just like this one. This one's a linear function with arrows going up and down forever and left and right forever. So our domain and range are both going to be all real values with no conditions. This one, however, we have conditions. Right? It touches that point but stops. It touches this point but stops. And these are examples that you can see in the real world. Real world examples don't usually go on forever. So if we're going to look at the domain, well, again, it's a continuous function, right? In between these 2 points, it exists everywhere on that line, right? It's not discrete. So we can say it exists for all real values, but we need a condition. So since the domain is our x, right, it looks like it's between x equals 0 and x equals 7. So we would write x is greater than or equal to 0 and less than or equal to 7. All right, so looking at the range, right, again, it's a continuous function. So in between our conditions where the function exists, it exists for all real numbers. Right? And then our condition is from here all the way up to here. So from 0 to 50. So we write that y is greater than or equal to 0 and less than or equal to 50. All right, so situation 3, they don't give you the values, but it's in your textbook. They say to use TI-83 graphing calculator, but we're going to use Desmos. Okay. And let me just switch over to Desmos. So I've already done this one. So here are our points. You might not be able to see them because that line's in a way, but it's 0, 1, 2, 3, 4, 5, which represents the number of people. And this is the cost of the banquet hall for that number of people. So if you've never done this before, on a Desmos, right, there's a plus sign over here, and you would just click on that, and there's something right here. You won't see it in the video, but it says table. If you click on table, you open a new table, and you can plot your points. Now in this case, what I've done is I plotted my points, and depending on the situation, what the real world situation is, you could also do a line of regression, which is also a line of best fit. Right? In this case, it's a linear function. So you might want to say it exists everywhere, but you really have to look at the context of the real world problem, because the real world problem says 0, 1 person, 2 people, 3 people. So would you really go up to the banquet hall and say, yeah, how much would it be if I had 2.687 people coming? Right? That doesn't make sense. Why does it exist there? Right? So you wouldn't, in this case where you have discrete values, clearly discrete values, it's not really a continuous function. So you would write the domain as existing at, in this case, 0, 1, 2, 3, 4, 5. And you would have to write each of those numbers separately. Okay, and then you would write the range existing at these values as well. Okay, it's the difference between discrete functions that exist only at points and continuous functions that exist everywhere at those points. All right?